So that brings us to this concept of ionization energy, which is literally the energy required to extract an electron from the nucleus or from the atom itself. And so you think about that, right? There's this is the hydrogen atom, which has just one proton and one electron. So you've got this positive charge in the center and this minus charge. They're being held together electrostatically, which keeps the electron in the shell. So because it's stable like this, it requires some energy, typically in the form of light or a photon, to then remove that. And the exact energy value is what we call the ionization energy. How much energy is required to remove that electron and just zap it out into space or a vacuum out here. Ionization energy, we also we typically shorthand that as E sub lowercase I. So we start with the hydrogen atom with the nucleus and the electron, and what we're left with post-ionization is H plus and the electron. So how does ionization energy trend on the periodic table, going back to this idea of periodicity? Well, I think it should be obvious that anything in the group 1A column, which is represented here, this would be 1A, we already know that that constitutes atoms like sodium and lithium and rubidium, all things that really, really want to get rid of that electron. Why do they want to get rid of that electron? Because once they get rid of it, they don't have that electron in that outermost shell anymore, and they've gotten into the noble gas configuration, the much more stable lower energy configuration. So it should make sense then that it takes a lot lower energy to pull an electron off of lithium, sodium, or rubidium than it would to pull something off of, say, chlorine, bromine, or iodine. And so in general, the ionization energy, EI here, is going to decrease as we move down the periodic table. It's already lowest when you're up here, but it's already low when you're up here. It's lowest though when you get down to this bottom part. Why does it get lower as you get down here? Well, the atom gets bigger and bigger and bigger, and those electrons are further and further away from the nucleus. They're way out here, they're really shielded, and so it doesn't take much for a photon to come in here and pick that thing off. And so remember that the atomic radius gets big as you go down here. So atomic radius gets big as you go down here. The further that outermost electron is from the center of the nuclear charge, the easier it is to pick off. And so elements down here in the periodic table have really small ionization energies. In contrast, the ionization energy gets higher as you go from left to right, and that makes general sense, right? If you go all the way to the right to, say, the halogens in chlorine, bromine, and iodine, these things want to accept electrons. They don't want to gain them. And so, I mean, they don't want to get rid of them. They want to go from chlorine to chloride, because then that gives them the noble gas configuration. And so these don't want to get rid of an electron, they want to accept one. And the same is true for the noble gas configuration over here. These are even harder to pull electrons off of because they're already really stable with full shells. And so it makes sense that the ionization energy is really just a proxy for the propensity for an ion or a cation to form. And this tracks as we look at how the ionization energy moves as you move up in atomic number here. So we can demonstrate this difference in reactivity by just looking at, or the difference in ionization energy as you move down the periodic table. If we just look at that group 1A set of elements and we look at the reactivity of water. And so I'm going to show you a really old YouTube video, but it's a good one, that walks you through the addition of lithium, sodium, potassium, etc., and their corresponding reactivities with water, which should give us sort of the same notion or it should reinforce that periodic table that I showed before, which showed how the ionization energy, the energy to remove, that gets smaller as we move down the table. In other words, it gets a lot easier to liberate it, which means that it gets more explosive. So let's watch this for a second.
Now, you may have been allowed to mix very small amounts of lithium with water. You may, if with a responsible adult, have mixed H2O with sodium. And you may, under very strict scientific control, have witnessed potassium mixed with water. But the odds are, if you have, it will only ever have been on one of those rubbish science videos. There you go, mate, present. These next two are the dog's nuts of the periodic table. They are, if you like, the king and queen of alkaline metals. Mix these babies with water, stand well back, and watch the mayhem. And that's just what we're going to do. Mr. Tickle, bring on the rubidium.
Here it is.
Is that it?
Well, it might not look like much, Richard, but it's a highly reactive metal. It's sealed in this glass tube under argon atmosphere conditions, just for safety.
Right, so what's going to happen when you drop that in the water?
Well, imagine, if you will, letting off a hand grenade in a bathtub.
Righto, I'm off. Have that.
Okay.
Good luck. Okay, Tickle. Drop the rubidium in the water.
Stand back, everybody. This one's going to be bad.
2 grams of rubidium will only react when our specially designed vial dissolves in the water, which gives John a few crucial seconds to get into our safety zone. Yes! Where hits the water. Imagine a depth charge in a bathtub. Fair enough, mate. I'll leave you to it. Good luck. Thank you.
So this last one is cesium.
Okay, John, go for it.
Warning, warning, warning. Extreme danger. Clear the area.
As our cesium sinks in the water, the rapid generation of hydrogen gas should produce quite an explosion. And it does.
So the general periodic trend for ionization energy is shown in the figure here to the left. So you can see ionization energy plotted as a function of the number of protons, or the atomic number. And if we start with, let's just start with lithium first. Lithium here and lithium on the periodic table over here. You can see this general trend as you move across the row is that there's this increase in the ionization energy, and that's what we'd already sort of alluded to. But there are a couple anomalous, always anomalous things that don't fit within the general rules. And so the first is this group 2A elements here. So group 2A elements, so things like beryllium, magnesium, calcium, so 2A being this group right here, they have a slightly larger ionization energy than necessarily the trend would predict, right? So you go from lithium and it bumps up, but then it comes back down for boron. So how do we explain this phenomenon? Well, if we look at the electron configuration down here for both beryllium and boron, so that's going from the beryllium state, or the beryllium atom, to boron, you see this dip. How can we look at the configuration and rationalize this trend periodically? So beryllium is nice. It's got this 1s2, 2s2, right? It's got the second subshell filled here, but then if we pop an electron off, so -1 electron, we're going to steal that electron from this nice filled 2s state. And that's going to require almost 900 kilojoules of energy for every mole of beryllium. But if we compare that to boron, so we hop over into the p group now, you can see that the electron configuration, as expected, would be exactly the same, except we've got that extra electron out in the first 2p orbital. Now, when we want to remove that same one electron, it takes a little bit less energy, right? Almost 100 kilojoules per mole less energy. Why would that be? Well, you can think about the sort of center of charge, the nucleus, on either of these atoms where the protons reside, and then you've got the sort of 1s orbital here, you've got the 2s orbital here, and then you have this big 2p orbital that boron has. And so you've got an electron here and electrons in each one of these. Which one of these orbitals is going to have a greater Z effective, or in other words, which one's going to have a stronger draw, or in other words, a weaker draw as well. And so you can sort of, in this hand-wavy explanation, you can see that this bigger orbital that's further away, that's incomplete, there's only one electron in it, that's going to be easier to snag and ionize than necessarily one of these electrons in the 2s state. And that's a really simple explanation. The Z effective is less felt out on this 2p orbital than it is by the 2s orbital. And that's why we see this characteristic dip between the group 2a beryllium and the group 3a boron. And the same can be true if we go from sodium to magnesium. We see, or not sodium to magnesium, sorry, magnesium to aluminum. So we go up and then we go back down. The same thing. In that case, we're going from 3s to 3p. Same rationale. And the same thing would be the same thing would be true for calcium. We go back up and then we dip back down again. Okay, so let's look at this other case then. If we look at the trend in the periodic table, as we'd mentioned before, the general trend is as you move across the row, the ionization energy is going to increase. It's going to get harder and harder to pop an electron off. And we saw that for group 2a, based on the electron configuration going from an s to a p, we get this little jump right at the break here, where we transition from a full 2s set, or a full s set, to starting to add electrons into the p set. And then if we look here, we have another anomaly which happens from nitrogen to oxygen, where instead of having this sort of monotonic increase here, we actually see it go down instead of go up. So group 6a elements, so that's over here starting with oxygen, pointing right there, they have a slightly smaller ionization energy than might be expected. So let's again use what we know about electron configurations to see if we can ascribe some sort of rationale for why this might be the case. So let's look at nitrogen, and then let's look at oxygen. So nitrogen is the one that's following the typical trend here. So I'll highlight this in a different color. So we're comparing these two elements. So for nitrogen, we've got 1s2, 2s2, and then 2p3, right, 2p3, 2p1, 2, 3, meaning we've got one electron in each of the 2px, y, and z orbitals. In that case, it's perfectly half-filled, right? We could write this out as the 2p, we've got one electron in each in its valence state. So if you're going to remove an electron from this and ionize this, that means you're going to have to grab one of these electrons out of the half-filled 2p orbital set. Okay, now let's compare that to the oxygen atom, which you're just moving over one in the periodic table, and that means you've got one extra electron to fill into your 2p orbital, which means that this 2p state will have 1, 2, 3, and 4. Okay, so which one of these is going to be easier or harder to remove? Well, you sort of got two lines of logic here to employ. Well, one is we'd already learned that several atoms will actually take on anomalous electron configurations in order to achieve a half-filled orbital, their subshell. That's net stabilizing, meaning it's a lower energy configuration to have a half-filled set than a set that's that only has 2 or maybe 4 or 5. And so this is good. Atoms like a nice half-filled set, so trying to yank that one out, that's going to be a destabilizing force, which means it's going to take more energy to do it. It's happy like that. We can also think about this in terms of sort of Hund's rule and thinking about electron repulsion. So in oxygen case, we've got two paired electrons in the same subshell, in the same actual orientation, in maybe the 2px here. These electrons are both negatively charged, right? Now you've got two negatively or identically charged objects that are going to experience a repulsive force that are right next to each other. Meaning getting rid of one of these and yanking that out is actually going to be pretty good for two reasons. One, you're going to get rid of that repulsive force, and two, you're going to re-achieve the half-filled set of oxygen that we know to be stable. And so if we look at the ionization energies, that's reflected, right? It takes more energy to remove an already half-filled set than it would take to remove an electron from oxygen, which would actually arrive at a half-filled set. And so what we're trying to do here is not memorize these rules, but really start to think about the relative energies and the stabilities of electrons in orbital sets, and use that to rationalize what we actually observe in real life. So let's look at a few examples here and see if we can use our knowledge of electron configurations to predict, and our knowledge of periodicity to help us predict which one of these two elements, these pairs, is going to have the largest ionization energy. So pause the video and think about what we know about periodic trends and electron configuration to try to assign some of these. And when you unpause the video, I'll have these already worked out. Okay, so I've got these worked out. If we look at the first pair, potassium and bromine, we know from our periodicity and from electron configuration as we move across a row, so potassium is right here and bromine is right here, so they're in the exact same row. We know that ionization energy increases. It gets harder to remove an electron as you move across the periodic table. They're in the same row, so we can rationalize that. We can also say that potassium has a 4s1 electron, right? Once you get rid of that, now you've gotten rid of that entire extra subshell. You're back into this nice noble gas configuration. That's a really happy state. So that means potassium is really easy to ionize, which means bromine is going to be harder. So two different sort of ways to rationalize that. Let's look at sulfur and tellurium. So sulfur, let's do a different color. Sulfur is right here in the table, and tellurium is right here. So they're in the same group. We know that the ionization energy increases as you go up a group in this direction. That should make some sense because just thinking about atomic radii, as you go down the group here, the radius gets much bigger, right? If the radius is bigger, those electrons in the valence shell, in that highest principal quantum number group, they're much further away from that core nucleus. So we're talking about comparing, say, sulfur, which could be this big, and tellurium, which could be this big, and both of those has a valence electron out in this shell. They both have the same exact electron configuration, except that tellurium has in the fourth shell, actually the fifth shell, and sulfur is in the third shell. And so which one of these is going to have a stronger Z effective charge? Well, this one, right, it's closer to the nucleus, meaning it's going to be held tighter here than it would be on this side. So this one's going to be easier to grab, which means the tellurium is going to have a lower ionization energy. It's easier to remove. In other words, sulfur is going to have the higher ionization energy. Okay, so the last two, let's look at gallium here and selenium here. So these are, again, we could rationalize it as you move left to right in the periodic table. The ionization energy goes up. That would be true, and that would get us to the right answer. We could also look at their electron configurations here. These are closed shell configurations. We can see that if we yank an electron from either of these, if we yank it from gallium, it's going to come from here. And if we yank it from selenium, we're going to grab it from here, that's going to get rid of this whole 4p subshell. That's a pretty net stabilizing force. In this case, this is going to result in a 4p3, which is still a half-filled shell, but that's going to be less stabilizing than just getting rid of that shell entirely. And so either way we want to rationalize it, the selenium is going to have the higher ionization energy. Alright, one more bit about ionization energies is this question of can we remove more than one electron from an atom? And the answer is absolutely yes. We call these higher ionization energies. So what happens if we want to pull 2 or 3 or 4 electrons out of these? Generically, we can write that as maybe some m, we'll just say m for a metal, plus some energy. That's going to pop an electron off like this. This is what we've already been accustomed to thinking about, and we call that the ionization energy. But here we're going to call that ionization energy 1, so that we can say, well, what happens if we take this ion that we just created and we say, let's yank another electron out of it. So let's add some more energy to it, and that gives us M2 plus another electron, and then we're going to call that the second ionization energy, and we could do this plus energy, make M3 plus, etc., and we could continue down this road, obviously just removing one electron each time as we do this. So this is the concept of higher ionization energies, or removing more than one electron from the same atom or ion. So when we're thinking about these multiple ionization steps, generally we think of this rule that each successive electron that's removed is going to require actually more energy because of the attraction of that electron to the positive ion. So let's think about that in terms of our generic case here. So in this first example, ionization energy 1, we're pulling a negative electron out of a neutral atom. Okay, so that's going to require some amount of energy. But if we think about the second step here, now we're pulling out an electron that's negatively charged, but we're pulling it away from a positively charged ion. So on top of the already high binding energy of that electron in its orbital, now we have this additional attraction between the positive and the negative particle that we're trying to remove. And this becomes exacerbated if we move to the removal of an electron from an M+2 ion. Right now we've got an even higher ion charge and we're trying to pull a negative electron out of this. So in other words, the ionization energy 1 is always going to be greater than, ionization energy 3 is always going to be greater than ionization energy 2, which is going to be greater than ionization energy 1, etc. And that's simply because each time you're pulling off that subsequent electron, the charge on that positive ion is getting larger and larger and larger. The attraction is higher and higher, meaning it's going to take more energy to remove it. Let's think about this with an example. Let's use sodium. So keeping an eye on sodium's up here on the periodic table. This is an easy one. So this is group 1A. So sodium 0, that's the elemental version, has an electron configuration of 1s2, 2s2, 2p6, and then 3s1. So 3s1 is that electron in that group right there. We can add energy to that system, and we get this sodium plus ion, which is 1s2, 2s2, 2p6, plus that electron, right? Okay, so this would be, let me slide this up a little bit. Oh, that's not going to move. Anyway, this will be our EI sub 1, or ionization energy sub 1. If we take this ion and then we remove an electron from that, so I'm just rewriting that electron configuration for the sodium plus ion, then we can think about what the energy would be for the second one. Now, we're trying to pull an electron out of. In this first one, I had highlighted in red, we're yanking that electron out of that 3s1, right? So getting rid of that electron actually makes this thing quite a bit more stable, because we no longer have that electron dangling out in that much larger third shell. Now, with sodium plus, we're trying to remove an electron from this tight already complete shell, which essentially is a noble gas configuration at this point, right? Because once we remove that, this now has a noble gas configuration of neon. So this is equivalent to the neon closed shell configuration. So we know noble gases are really, really stable because they have this nice complete shell. So now we're trying to yank an electron out of that. Of course, that's going to take more energy, so we'll end up with sodium 2 plus with 1s2, 2s2, 2p5. So we're actually pulling an electron out of the next lower shell and destroying a noble gas configuration. So you can make the prediction here that the second ionization energy is going to be much, much larger. It's going to take a lot more energy to remove that than it would in the first time. And in reality, it's about 10 times the amount of energy. So if it took, let's say, 1,000 kilojoules per mole to yank off the first electron, it might take 10,000 kilojoules per mole to yank out the second. And the whole reason for that is based on the change in these configurations, what's stable and what's not stable. And so disrupting a noble gas configuration really never happens. And that should make sense. And that's the whole reason why we call these things noble gases, is because they have an already filled shell. There's no reason for them to add or remove electrons. They're already as stable as they can be. And so if you get an ion that forms and that takes on a noble gas configuration, it's super stable. And our intuition should make some sense here, right? We know of sodium to be super stable, right? We put it in our food as sodium chloride, and we're not worried about it spontaneously oxidizing and removing a second electron to become sodium 2 plus. It's also why you've never heard of the ion sodium 2 plus, because it doesn't really exist. Maybe in the lab you could create this, but it would instantly revert back to sodium plus to achieve the noble gas configuration. So we're sort of alluding to a major general principle in chemistry, which we're going to talk a lot about here in subsequent chapters, which is how do atoms and ions achieve a noble gas configuration? All atoms and ions are going to react in the periodic table in order to achieve this configuration. And we're going to get to a point where we start to name this thing. We'll call this the octet rule. And so I'm foreshadowing here, but we'll talk about this in the next chapter.